Hi everyone, this is Minji Lee and I present a paper named SimMIM, a simple framework for mask image modeling, which is presented at CVPR 2022. Mask image modeling is an image self-supervised learning technique that aims to learn representation by predicting the mask tokens given the visible tokens. This approach is inspired by mask language modeling, which has shown remarkable performance in a broad range of NLP tasks. However, the setting of the mask image modeling should be different from MLM, considering the inherent differences between the visual signals and text tokens. Let's go one by one. First, an image exhibits a stronger locality than the text. In other words, predicting mask pixel can be done by seeing nearby pixels. Thus, the masking strategy is important in MIM. If the masking is trivial, the model will reconstruct the image using nearby pixels, rather than understanding the semantics of the image. Second, image is a raw, low-level signal, whereas text is human-generated, high-level concepts. We can expect that the model would learn high-level concepts such as grammatical rules from the mask language modeling. However, it is unsure if the prediction of low-level signals enable the model to learn representation that are useful for high-level visual recognition tasks. Third, image pixels are continuous, whereas text tokens are discrete. Classification-based MLM framework is not directly adaptable to image modality. This raises the need of decoder architecture or a framework suited for images. Let's see the three aforementioned points in a unified view. So, when designing a mask image modeling framework, we should consider masking strategy, decoder architecture, and prediction target. Motivated by these points, the paper introduces a simple yet effective design that aligns with the nature of visual signals. The authors compare their simple framework with the complex design proposed before. Authors propose patch-aligned random masking, where each patch is either fully masked or fully visible. This strategy is convenient to integrate with the VIT framework, which processes the image into patches. This is also much simpler than block-wise masking proposed previously, which repeats to mask the image with the mask of random size and random aspect ratio until reaching a desired masking ratio. Authors compare various masking on the fine-tuning accuracy on ImageNet classification and show that their random masking with the large patch size of 32 is the best performing strategy. They define FDIS metric, an average distance of mask pixels to the nearest visible pixels, to compare the strategies. Small distance may let the network learn too short connections, while large distance may be too difficult to learn. FDIS should be moderate, as in proposed patch-aligned random masking. The pixel values are continuous, so a straightforward target is to predict raw pixels of the mask area by regression. Previous methods propose additional tokenization networks or binning methods to change the problem into classification. In this paper, authors propose Allen laws on mask pixels. You can see from the table that the color clustering, binning, or tokenization performs slightly worse than or similar to Allen laws. It shows that it is not necessary to use the same classification-based target as mask language modeling. It is good to align the target to the own nature of visual signals. Lastly, the authors compare the different decoder architecture with respect to top-on accuracy, number of parameters, and training cost. The table shows that the decoder can be extremely lightweight, as light as a linear layer. It achieves the best performance while about 2 times faster to train than complex decoder models. SimMIM shows state-of-the-art accuracy with all methods combined, with much lower pre-training cost. Finally, the visual results demonstrate that MIM learns the semantic of the image, not simple copying of nearby pixels. Even if the most parts of the major object are masked, the model can still predict the existence of the object and reconstruct the object. To wrap up, SimMIM introduces a simple yet powerful framework for mask image modeling that is composed of patch-aligned random masking, a one-layer decoder, and a pixel regression target. These components are designed to align with the nature of visual signals and thus highlight the potential of the mask modeling approach in the computer vision field. Thank you for listening.